I used his answer book because I looked at it with him.
All right, we talked about this vaguely a couple days, so I feel like I can just go over this quickly. Hey, listen. Quickly means you need to listen now. I think in regular chemistry we had 6 postulates. They've kind of abbreviated a couple together, so there's only 4. So not quite as much, but you should remember. Okay, we already talked about this. Particles are so small compared with the distances between them that the volume of the individual particles themselves are assumed to be negligible or 0. Remember, that was an assumption. That assumption led us to believe that if I have a mole of particles, my volume is what? What is that constant number? 22.4. But then I said that's under ideal situations. What needs to be true for this to be a good approximation?
High temperatures and low pressure.
Well, this one is just one of them.
High temperature.
Low pressure.
So here's what needs to be true for for one to be correct. You've got to have low pressure. Okay? What happens when you have high pressure? What we talked about this. What happens when you have high pressure?
The particles are closer together.
Okay, great. What does that have to do with that?
So it's not negligible.
Yeah, because if the difference in the volume of the actual particle itself is fairly small, and when most of the volume is just the open space, it's so small that it's negligible. But when you start pressurizing it and you reduce the volume, now the volume of the particles plays an important part. Okay? All right, second one. Particles are in constant random motion. Collisions of the particles with the walls of the container are the cause of the pressure exerted by a gas. That makes sense? Particles run into the container, collide, exert a force over an area, you get a what? Pressure. Pressure is force over area. Okay? 3. Particles are assumed to exert no force on each other. They are assumed to neither be attracting each other nor repelling each other. And only for this to be true, you have to have
High temperatures.
What happens if you have low temperature?
They won't be.
They'll be
moving slower than they may attract each other.
They'll move slower, they'll start attracting each other, and they won't go in nice straight lines, and so therefore that's going to affect the amount of collisions they have with the walls, won't it?
Yeah.
If it's not just going in a nice straight line, that curved motion is going to affect how many times it hits the walls. What will that affect? Pressure. Okay? So this one really affects pressure, and this one really affects the volume. Okay? Last one. Average kinetic energy of the collision of the gas particles, collection, is assumed to be directly proportional to the temperature. And we know this because, by definition, what is the definition of temperature? Average, yeah.
Kinetic energy.
Average kinetic energy, okay? So if kinetic energy goes up, what goes up?
Temperature.
Temperature. And the movement of the particles go up. Okay? Now, we know that these are the conditions for an ideal gas. These don't really match real gases or what we would typically see. However, if our gases, our real gases, are under these conditions, they act ideally. If they're not under these conditions, they don't act ideally, and we cannot make all the approximations and do all the nice, helpful gas laws that we've been doing up to this point. Make sense? Okay, just a quick little review here. Okay. How about this? There's your Boyle's law, which we said is P1V1 equals P2V2. What was constant in this situation? Do you remember?
Moles.
And?
Temperature.
Yes. Okay? So you can imagine, if you take this guy right here, notice how I have 5 particles on both sides, same amount of moles, right? Okay? And I decrease the volume. What is that going to do to the pressure? Increase it, because you're going to have more collisions with the walls per unit time. Okay, makes sense? That one's harder to see. Gay-Lussac's law. What's held constant in Gay-Lussac's law?
Moles.
Yep. Nope.
I can't see the words.
Nope.
No, that's it.
Volume.
I can't see the words.
Pressure over temperature is Gay-Lussac's law. So moles and volume are held constant. You can look at the volume. Held constant. And you can count all the particles and see that there's the same amount of particles. But what this is trying to show you, probably can't read that. Can you read that? So it's 75 Kelvin, 150 Kelvin, and 300 Kelvin. So what's happening as I go left to right? What goes up?
The temperature.
Temperature goes up. Increasing temperature is going to cause the particles to what?
Speed up.
Okay, move faster, probably collide with the walls of the container more. And if the volume isn't changing, what is the increased motion causing more collisions with the wall of the container going to do? Increase the pressure. So if you remember, this is a direct relationship. Pressure goes up, temperature goes up, and vice versa. Temperature goes down, pressure goes down. All right, Charles' law. This one's trickier because the volume has to change in order that something remains constant. So what are the 2 constants in this situation?
Pressure.
And
Moles.
moles. Should have the same amount of moles here. Okay, as you heat it up, we know heating up would make the particles move faster and collide with the walls more, right? Increasing the what? Pressure. But in order for the pressure to remain constant, what has to change so that the pressure stays constant? Volume. Because increasing the volume is going to reduce the amount of collisions with the walls and thus keep the pressure where it needs to be. Make sense? All right, almost done. Diffusion.
Oh, remember this one?
Tiny orifice. Alright, so diffusion you should know, mixing of gases. Really you could say mixing of anything that has the ability to flow, so you could say diffusion happens in liquid particles too. Okay? It's really how fast your in this case context, gas particles move through other gas particles. When we smell stuff, a lot of applications of this. Heat fusion is similar, but slightly different in this. Diffusion usually is really easy because you're diffusing through really open space, because gas particles have really open space. Heat fusion is taking a gas particle and squishing it through an orifice, or aka a really small hole. Okay? Best example that I think just does the best job of explaining this is what happens to a balloon over time. It does leak air, right? It gets small over time. You guys all have experienced it. It happens. Okay? What's happening is the gas particles are getting through the small little holes in between the solid particles, and voila, you lose air.
Especially helium. It's small.
So the orifice
Not
is
small size.
the
It's so small.
I guess.
Well, carbon dioxide is a lot bigger than that.
Well, carbon dioxide. Well, I guess if you're blowing it.
Yeah.
Okay? Actually, I still think most of it is nitrogen.
Okay.
Because you suck in
Yeah.
78% or 79% nitrogen. Your body does nothing with
Well, N2 is still a lot bigger than
it. Yeah. Okay? And here's a little law Mr. Graham came up with to really kind of determine how the rate of fusion of a gas is really dependent upon its molar mass. Why do you think it's dependent upon molar mass?
the size.
It's the size of the particles, like Ryland was saying. Okay, helium balloons actually have to be put in this, I don't know, different material. You guys know helium balloons usually are in, I don't know, this different. It's a different material that you probably. You know what I'm talking about? You go to get those helium balloons.
It's a shiny.
It's like a shiny, like.
Oh, is it like the aluminum?
I don't know if that's what it is.
I don't know either. I just do it with aluminum.
Yeah, I don't know. But you guys know what I'm talking about.
Yeah.
Helium balloons usually are in a different type of container than just like a regular balloon you would blow up.
Those ones last a lot longer.
Yeah, and it's because it must be, it has something to do with the properties that makes effusion a lot more difficult. Okay, because like Ron was saying, helium is going to effuse a lot better than carbon dioxide or any of the other gases simply because of its size.
By hydrogen, it's hard to.
That's why we'll talk later, when we talk about alternative fuel sources, hydrogen is very difficult to transfer or transport because it can effuse into metals and actually start weakening metals, and then you got a problem.
So how did they hold it in giant airships?
Well, they did it once and it blew up, and then they don't do it anymore.
Oh, they only did the ones.
Oh, I don't know.
Like I know the Hindenburg blew up. Yeah.
Yeah.
That would be cool.
Yeah.
Was that like on TV?
Hindenburg? It
Uh,
was during World War II, so probably the German team.
Like, that would have been so bad just like watching that like going up and then like.
Yeah, it was a German.
It's like 9/11.
Karen
Yeah, it's literally
It
like
was a
that.
German airship.
Only watching it on the air.
Okay, so here's the only thing that I will say about this.
Okay.
Is you gotta be opposite sides here. One on top, one on bottom. And whether you choose one of them, how you know which gas to go with what, just as long as you have the effusion rate and the molar mass together as the ones. Does that make sense? So, you guys do this and then we'll be done. Yep. So in this problem, they're just asking for your ratio of effusion. So they don't give you the actual effusion of any of the guys, they just want your ratio. So essentially you're just taking the square root of your two molar masses and dividing. 300 what? I mean, we've been kind of doing a lot of that in this chapter.
Where's your ratio?
Yeah,
That's what I want to know. Like, what?
92, bottom, very bottom.
Oh, that makes sense.
Okay. No,
What's the
Yeah, I knew that.
there is a unit number, it's a ratio. When you guys get this ratio, I'm curious if you can explain what that number tells you.
You're gonna come to our power club game?
I'll vote you if you want.
Yeah, give me the seniors.
I want to announce, that sounds awesome.
He's announcing with Steven, and they're wearing suits.
Never gone.
I can be crazy as a coach.
Yeah. You beat Coach, yeah.
Wait, are you coaching golf, right?
Probably not.
Golf? You golf?
I did. Not nice, not like, I only golfed 1 year for a team, but like after I got my first 2 years in college, when I went to play at Division I junior college in my hometown, I had nothing to do, so I golfed all the time.
Yeah, that should be 333.
Like I was like, please get an age.
92. Plus extra 4. Oh, I didn't see
Is it
that.
like easier than high school?
Dude.
I don't know about that. I still taught, it was, the school I went to was actually a school of science, so it was like known for being at least decently good in science. So I had to work in my science classes. Just one time I took a business class and I had 108%, like three quarters of the way through the year, and I didn't do any homework the last quarter and still got an A.
Oh,
Yeah.
what did you go for?
I got a chemistry degree. But at that point I was doing pre-med.
How do you avoid homework
5% going into it.
Still, that got really fast. I mean, Simon.
When did you go to
Not-
Cairo?
When did I want to?
Yeah.
Right when I started college.
So that's what pre-med was.
Yeah, I was doing pre-med so that I could go to chiropractic school. What'd you get for an answer, guys?
0.07.
That's all I have. What did you get credit on to?
Guess it doesn't matter where you put it.
I got 12.8.
I got 13.2.
Hey, 12.84 is the closest.
You put 52 on.
Still wrong.
352 over 2.016.
How do you know what goes on top?
Helium's not diatomic. Who said helium?
Hydrogen gas.
Oh.
I guessed what the
Wait, how is it
mass
thir-
was for
wait.
the second one? For 360.
Wait, how do you do it?
Write it on the board. What did you get for the molar mass of?
352 and 2.02.
352. I got 333.
You really
I'd say
struggle with
6.
molar masses, don't you?
Wait, so you have to put
Ah.
Here's what it looks like. I don't know if this is true. I don't know if this is always true, but it appears that you need to put the bigger molar mass on top.
Yeah.
Always.
Everything I'm seeing so far is suggesting that. So, yeah, in the one example in your book, it's the same thing. I do want to have you turn to 214 to end today.
So it looks like 13.2. Is that the answer?